All right, so let's try this problem. See what happens.
It was CY is 1.25 and AY is 0.25 kilonewtons.
All right, so yeah, I'm going to shortcut it. Everybody get that? Does those numbers sound familiar? So I'm just going to write them in here. So AY was what? Was it, Mr.
0.25 kilonewtons.
0.25?
0.25. 0.25.
And then CY was
1.25. 1.25.
Really?
Yeah.
Oh, I see it now. I saw this load in Solve 3 and thought it should be 4.5. I almost made a big mistake. All right, so that'll help us get started. And like I said, in a lot of these problems that we do up here, we'll assume that you can handle the initial reactions. So what I'm going to do is I'm going to go ahead and draw my lines for my shear moment diagram template. I seem to have kind of a line on there. There's going to be probably something happening here as the load transitions from 0 to that, so I'll go ahead and add that line into the mix. And then I'll create a positive x-axis and a positive axis for shear, and all my numbers will be in kilonewtons. So starting from the left edge, what's my shear? Well, my load there is 0.25, and what kind of shear is that? Positive. So I'll start at 0.25. Now remember, our basic rules are that the change in shear is the area under the load diagram. And what is the area under our load diagram? From 0 to 2? 0. So that should not change. And the second relationship from this set is that the slope of the shear diagram should be equal to the loading. And what is the value of the load between A and B? 0. So that means the slope is 0. That means horizontal line. So we have a section of constant shear over the first 2 meters. Now what happens from B to C over the last meter? Well, again, change in shear is equal to the load. Now what's the area under the load curve? Yeah, 1.5 times 1, and that's positive or negative? That's a negative load. So I'm going to have 1.25 minus 1.5 gives me, I said 1.25, I meant 0.25 minus 1.5, and that brings us to our 1.25 value here. And it's negative, and you go up here and look at that, that is negative shear. What's the shape of the curve? Well, the slope of the shear diagram is the load. So we go up here and look at the load. What's the load between B and C? It's constant. So we have a constant slope, and it's a negative value. So we have a constant negative.
Is it important that the line crosses at the midpoint of the load?
It does not cross at the midpoint.
It does not. I thought we, like, if you were to cut it at the midpoint right there, would it not be
Midpoint of what?
between B and C?
Okay, if I cut it here and do what? Try to find the internal moment?
Would it not be positive on the left side of it and negative on the other side of it?
What are you talking about?
Like if you were to draw, you know how you drew your one vertical line, if you were to draw another vertical line, would it not intersect right there? Do you understand what I'm saying?
No. I do need to know where this point is, but it will not be in the midpoint.
Okay. All right.
So now that I know that it crosses, I need to add another line to my template for moment. So now I have 1, 2, 3 sections for moment. I think that's what started this whole process, is how to handle that. Mr. Romero said he wrote an equation, which works, but it kind of defeats the idea of this graphical technique.
So you weren't expecting us to actually calculate the point where it crosses?
You do need to find that point. So I'm going to call this point right here, this distance, I'm just going to call it x1. So what is x1? Okay, let's use our relationship right here. It says the change in shear between 2 points. Okay, which 2 points are we interested in? What's the change in shear between this point and this point? The shear starts at 0.25 and goes to, so that's a change in shear of minus 0.25 kilonewtons. Simultaneously, what's the area under the load curve in the same position? So if I project this back up, this is now my x1. What is the area under this part of the curve?
1 minus x1.
It's minus 1.5 times x1. And those two things are equal. Right? Change in shear equals that. So that means I write the equation 0.25 kilonewtons should be equal to minus 1.5 x1. So what's x1? Whatever that is divided by 1.5. Pretty small. One sixth, right? So 0.167, and that's meters. So, how's that? Is that better than writing the equation?
Yeah.
That'll always work too. As long as you can go back up to this diagram and find the area as a function of the thing that you're interested in, that distance x1, you're okay. So for a constant load, it's no problem. For a triangular load, you'd just be 1/2 base times height. For a trapezoidal section, you'd have to average the height, but it's still times the base. Okay?
So you always...
You don't always, but I mean, I'm just using what I already have, and I'm kind of focused on the fact that I want you guys to use these things. When you think about drawing a shear moment diagram, all you have to remember is that, and apply it.
Well, I didn't find any critical points. I just went. Like,
Well, if you don't find this point, you don't know where the next moment's going to show up. Right? Let's do that. So the moment is what? What's the moment at A? 0. So I know I'm going to start here. What's the moment at C? 0. All right, now let's apply our relationship for that, which are the same, just bumped up. So I know that now the change in moment is the area under the shear diagram. And of course, the slope of the moment diagram is the shear. So let's start first with change in moment. So change in moment is equal to area under the shear diagram. So let's look at this section here from 1 to 2. So the change in moment, I'm at 0, changes to point B. That change is equal to the area under this diagram. What is that area? Well, it's 0.25 times 2. Right? That's 0.5. And that's positive area. So I have a positive change. So I go here and I get, what did I say? 0.5. Okay? What's the shape of that curve? Well, according to this, the slope of the moment diagram is equal to the shear. What's the value of the shear here? Positive 0.25. What's the value here? Positive 0.25. You can see it's constant. Positive. So you get something like that. In fact, if you actually checked it out, you would see that it is 0.25 to 1. That's the slope. Okay? Now, what's the change in moment from here to this distance x1, which we've solved as 0.167? What's the change in moment in this little interval? Well, if you follow the equation, change in moment is what? Area in the curve. So what's the area of the curve right here? Right, so 1/2 base, which is x, which is 0.167 meters, times the height, which is 0.25 kilonewtons. What's all that? 0.021 kilonewton meters. Everybody get that?
Yes.
So that's a positive area. So I have to add it to 0.5. So that means I get a little bit of increase. So it looks like I got 0.521. Now it's going to be hard to see this, but if you look at the slope right here, well, it's still positive 0.25. But what happens is the slope, as you move to the right, the slope decreases to 0. So that means right at this point, which is hard to see, the slope equals 0. So you do get a little bit of a curve, and it flattens out. Now what happens? Well, now the change in moment, area in the shear diagram, so the change in the moment from this point to the end of the beam should be equal to the area of the curve. So this distance obviously is going to be 1 minus x1, right? Because that total distance was 1. So now the area under this part of the curve, I'm running out of space on my page, would be 1/2 base, which is 1 minus x1. What was x1? So that'll be 5.833. And then times the height, which is negative 1.25. If we're lucky, that should be negative 0.521. So if I have positive 0.521, add my change to it, I get to 0. Great. So now let's look at the slope. Well, the slope is given by the shear. So I start right here. The shear is 0, and it gets bigger and bigger negative. So that means I start off at 0 slope, and then when I get all the way over to the right-hand side, if I looked at that slope and actually computed it, it'd be a drop of 1.25 to 1, that value. So that means my curve might look something like that. So there's my moment diagram. So the question, which we can add to this, which is not the original question, so where's the maximum moment? Well, it's 0.521 kilonewton meters, and it's located at that point, which would be at x equal to 2.167 meters. Right? At this point right there, which would be the 2 plus our little difference. Any questions about that? This is a very testable type problem. I think this is very doable in the 15-minute window.
So did we just find the max just to know?
Well, you want to know the maximum moment because that's going to drive your design of the beam from that point on. And it's also important to know where it happens. If you were to design this beam, and let's say, for example, this beam just happens to be pieced together here by 2 pieces and you want to put a connection here, you're going to tell yourself, well, that's not a very good place because the moment's very high there. If you want to put a connection over here somewhere, that's a better place. The moment's much lower. So it'll give you some characteristics of the structure under the load and tell you how you might want to handle the design. But at a minimum, you'll design your beam for the maximum moment. If this is a reinforced concrete structure, it might give you some ability to reduce your reinforcement. Over here where the moment gets low, you may not need all your reinforcement. So you could do what's called bar cutoff. And you'll need the moment diagram and the values in order to know where you can cut your bars. So our course isn't very exciting because we don't ever actually get to do any design, but our work is the fundamental. That's the basic things you need in order to do the next part. Okay? Any other questions before I turn this one down? All right.